Welcome back. In this video, we will continue our discussion of switching and bridging. In particular, we will discuss LAN switches. The contents of this video are learning bridges, spanning tree protocol, and virtual LANs. By the end of this video, you would know how switches learn the forwarding table and how switches avoid loops in extended LANs. Lastly, you will know how to partition an extended LAN logically. We are going to use these terms bridges and switches interchangeably. So LAN switches or bridges is a class of devices that is used to forward packets between LANs, right, such as Ethernet. So we have seen before that we may connect hosts to a switch, right? In this case, a switch is just forwarding packets from one host to another, but we can also connect a switch to another switch that in turn connects different hosts, and it's basically we have two LANs, so let's call it LAN 1 and this is LAN 2. The purpose of these switches, you can call switch 1 and switch 2. So switch 1 forwards packets from hosts in LAN 1 to hosts in LAN 2 and vice versa. Switch 2 forwards packets from hosts in LAN 2 to LAN 1. And a collection of LANs that are connected by one or more bridges is called extended LAN. There are basically three kinds of bridges, and they are not mutually exclusive of each other, as we'll see. So the simplest kind is called hub, right? This also some people would informally refer to as no frills bridge. And again, we have discussed hub before in one of the videos, right? So remember, hubs simply forward frames out to all other outputs. So suppose there is a hub, and just as a simple example, let's say we have 4 hosts connected to this hub, and so if A sends a frame that is supposed to be, let's say, delivered to C, but regardless of the destination, what a hub does is that it's going to forward an incoming frame to all other ports, and so it just does not send it back to the port that it receives from, but it just forwards to all other ports. And hubs were used as early bridges. They are very simple to design, and this is one case where we don't really call hub a switch, right? So we call hub a hub. In other cases, we interchange a bridge with a switch. And then there are what is called learning bridges or transparent bridges. So these bridges learn the presence of different hosts that are connected to their ports, right? So we will discuss learning bridges after the first thing after this slide. And then there are bridges that implement what is called a spanning tree protocol. IEEE 802.1d is a standard for MAC or layer 2 bridges, and the bridges that are compliant to this standard are required to implement spanning tree protocol. And note that, as I said, these are not mutually exclusive. So modern bridges implement both learning bridges and also spanning tree protocol. We are going to discuss learning bridges. Now, suppose we have these two Ethernet segments. So these are all classic Ethernet segments, and they are connected by a bridge. Right. So on the first segment we have hosts A, B, C, and on the second one X, Y, and Z. And suppose A sends a frame to B, right? So as you know, that's the case in classic Ethernet, right? This frame is going to be received by all the nodes, right, that are attached to this segment, right? So it's going to be received by this bridge also. However, in this case, bridge does not have to do anything, right? It does not have to forward it on port 2 because A and B are connected on the same Ethernet segment, right? So whatever A is sending is going to be automatically received by B. However, for the bridge to know that it does not have to forward, the frame on port 2, it has to learn, right, which ports connect which hosts, right? So on which side, right? So on which of the, for example, the hosts, it can reach via port 2, and which of the hosts it can reach via port 1. And that's the problem, right? So one option is that we can configure this by hand, right? So this information about which host is reachable via which port is basically part of what we call forwarding table. And so we can put these entries in the forwarding table of this bridge by hand, right? So as you can see in this example, right, these three hosts A, B, and C are reachable via port 1, and then X, Y, and Z are reachable via port 2. If the bridge has this information, and then if it sees a frame that is addressed to B and that arrives on port 1, it knows that it does not have to forward this on port 2 because B is reachable via port 1, right? So it's not on the other side. However, as I said, one option is to configure this forwarding table by hand inside every bridge, but as you can imagine, that's not scalable, and so we actually do it automatically, right? So how do we do it? A learning bridge learns the location of a host by inspecting the source address in the frames that it receives, and what it does is it records the source address and the port at which that frame was received, right? So this is what constitutes an entry in this forwarding table. So when a bridge boots, this table is going to be empty, and as hosts start transmitting frames, then this table is built gradually over time. When A sends a frame, regardless of the destination, so it could be any of these other 5 hosts, or it could simply be a broadcast message or a multicast message. Regardless, when this bridge gets that frame that A sends, it knows that A is reachable via port 1, and therefore this entry is created in its forwarding table. And so similarly, when X sends something, then the bridge knows that X is reachable via port 2. Now with all of these entries, there is a timeout that a bridge would associate, right? And if that entry is not refreshed before the timeout, then this bridge is going to discard that entry, right? And this is done to take care of the situation when a host moves to some other location, right? So in a situation where the topology of the network changes over time, again we need to have a mechanism so that bridge is able to detect and it's able to do the right thing. And so suppose, after some time, X moves from the segment 2 to segment 1, right? So there is host X over here. So either X sends something and bridge then learns that, X is now reachable via port 1, and so it will just change it to port 1. Otherwise, this entry is going to time out and it's going to be flushed out of this forwarding table, and then later on, whenever X sends something, then the bridge would just add this entry that X is now reachable via port 1. And there is a question, what happens when this bridge receives a frame for a host for which there is no entry in this table? And even before that, as we saw, when this bridge boots, this table is empty. So in our first example, A had sent a frame, right, to B. And so in that case, suppose at that time the bridge has just booted, so all these entries were just not there. So the result of that transmission would be that this bridge would know that A is reachable via port 1, but then, since these entries didn't exist at that time, right, there was no way for this bridge to know where B is. And so in those circumstances in which the bridge does not know, right, where the host is, it broadcasts the frame on all other ports, right? So in this case, what this bridge would have done is it would have broadcasted this frame that A had sent to B onto port 2, and hopefully after some time B would have sent a reply or some sort of a frame, and then this bridge would know that B exists and it's reachable via port 1, and then after that any transmission from A to B would not be forwarded on port 2, but until then the bridge would keep forwarding the frames to all other ports. And in an extended LAN, this is going to reach other bridges, and they're going to do the same, right? So every bridge does the same. And this is, when this happens, this is called flooding, right? So one frame is generated, and because these bridges don't know where to forward it, they keep forwarding on all the outgoing ports except for the one where the frame came from. And so in general that's all right, but in extended LANs, right, it may have loops, right? So here is one example. So we have bunch of Ethernet segments, and as you can see there, there are loops. So in this example, B1, B4 and B6 form a loop, right? That's one example. There are other loops. B1, B5, B7 form a loop, and then B1, B2, B3, B5 form a loop, and then also there's a larger loop, right? So but why loops are a problem? Loops are a problem because suppose B6 just broadcasts something, right? So it reaches B1. Now B1 is going to forward on all its outgoing ports, so this is going to be forwarded to all the other bridges. And just focus on this smaller loop. So this is going to reach B4. Now B4 is going to forward this again to B6, and so this is going to continue, right? As long as these don't know how to reach a host, right? So maybe that host either does not exist or it's outside, right, somewhere, maybe B. And so in the case of loop, when you send a broadcast or multicast, there is a danger that these frames would potentially loop forever, and as time passes, more and more frames would start looping in this LAN, and after some time they would simply exhaust the capacity of this network. Now you might be wondering why LANs have loops after all. So first is that networks, as long as they're not very small, they are managed by more than one administrator, right? So if there is no single person who knows the configuration of entire network, it's possible that there would be loops that would be caused by adding links, just because the person didn't have full knowledge of the topology. But more importantly, actually loops are built into the network by design, and this is done to provide redundancy in the case of failures. So given that loops are going to be there in extended LAN, what do we do about it? So the protocol that is used to detect loops and remove the loops is called a spanning tree protocol, right? And this is based on a spanning tree algorithm. It's a distributed algorithm that solves this problem. So we are going to study spanning tree protocol next. We will model switches by the vertices of a graph and the links that connect the switches as the edges of this graph. And so here is a topology where, as you can see, there are several cycles. So spanning tree is a subgraph of this graph that covers all the vertices but contains no cycles, and we achieve that by removing some of the links. So for example, we might remove this link and this link and that link, right? So that gives us one spanning tree, right? So here is another one. So the thing to note is that a spanning tree keeps all the vertices of the original graph but throws out some of the edges. And the challenge for us is to come up with a protocol such that all the switches of the network agree on one particular spanning tree. As I told you, there may be several different spanning trees that can be constructed out of a graph. The spanning tree protocol that is part of IEEE 802.1d standard is based on a spanning tree algorithm. This algorithm was developed by Radia Perlman, and if you want to know more about it, you can read her book. It's called Interconnections. The spanning tree protocol is a protocol that is used by a set of bridges to agree upon a specific spanning tree for a particular extended LAN. What it means is, as I said before, is that all the bridges would agree on one and the same spanning tree. The spanning tree algorithm is a distributed algorithm. So what it means is that each bridge decides which ports it is going to use for forwarding frames and which frames it's going to block on its own. There is no central coordinator that decides this for the bridges. So let us consider this example of three bridges. There's a bridge 1, there's a bridge 2, and there's a bridge 3, and there's a loop. And so what these bridges do is, when they run this spanning tree protocol, they are going to block some of the ports, right? So they're simply not going to use. So suppose this bridge 3 decides that it's going to block this port, right? And the result of that is that as if this link does not exist, right? And so automatically now we have a tree. The spanning tree algorithm is a dynamic algorithm. So what it means is that the bridges would reconfigure themselves into new spanning tree if some bridge or bridges in the network fail, or some link or a set of links fail. The bridges agree upon a spanning tree by exchanging messages, and the messages that are sent to form the spanning tree are called Bridge Protocol Data Unit, or BPDU for short. And bridges would send BPDUs periodically, roughly every few seconds. Although BPDUs have a particular frame structure, but for our discussion we are going to denote BPDUs as a triple, right? So it's going to be of the form B dot D dot E, where B is the ID of the bridge that is believed to be the root bridge at the time that BPDU is sent, and D denotes the distance of the bridge that is believed to be the root bridge from the bridge that is generating this BPDU message, right? And that bridge has this ID E, which is the third field in our triple, and E is, as I said, is the ID of the bridge that sent this BPDU. This algorithm relies on the fact that each bridge has a unique identifier, and in our previous video on Ethernet we know that the MAC addresses are unique by design. So basically first 3 bytes of MAC address is the number that is allocated to the vendor, and that the vendor appends another 3 bytes to make sure that this entire MAC address is unique. And in addition to that, there is a spanning tree priority field that is used. And so these two things together, the spanning tree priority field and the MAC address, right, ensure that every bridge has a unique ID. But in our discussion, we are just going to use these symbols B1, B2, B3, and so on as bridge ID. And in this notation, what we mean is B stands for bridge and 1 is the ID of this bridge, right? That's how we are going to compare. The purpose of using this spanning tree priority field is that a network administrator can configure a particular bridge to be the root bridge, as we'll see next. So in the spanning tree algorithm, the bridges elect the bridge with the smallest ID as the root of the spanning tree, right? So therefore, if the network administrator decides a certain bridge to be to be the root, then he can set up this priority field accordingly, right? So that's the purpose of this priority field. In this algorithm, upon booting, every bridge thinks that it is the root, and therefore it sends this configuration message which has this form as we saw before. So the first field is the ID of the root bridge, and since initially this bridge thinks that it is the root bridge, so it sends its own ID, and since it's the root bridge, so the distance to the root bridge is 0, and then is the ID of the bridge that is generating this BPDU. So that's the first message that a bridge is going to send. When a bridge receives a configuration message over a certain port, then the bridge checks if the new message is better, and we're going to define in the next slide what it means to be better than the current best configuration message that has been recorded for that port. And so we define a configuration message to be better basically in this order, right? So the smaller is better, so smaller ID is better, right? So that's the first field, and if there is a tie on the first field, we look at the second field. Again, the smaller is better, and if if both of these two fields end up in a tie, then we break the tie on the third field, and if there is still a tie, then we break the tie as depending on the port, right? So that's what is used to determine whether one configuration is better than the current one. So as I said, First, if a message that is received identifies a route with a smaller ID, then that message is better. So let's consider this bridge, let's call it B10. Let's focus on this port. And suppose the best configuration message it has received so far on this port is let's say B4 dot 4 dot B let's say B8. Okay, and so suppose it receives a message that has this configuration, so let's say B2 dot 5 dot let's say it's coming from bridge B7. And so although the distance shown here is larger than what it has, but it identifies a smaller route, right? So this message is better than the configuration, the best configuration it has received on this port. Now the second tie is that if the message identifies a route with equal ID but with a shorter distance, then that message is better. So it may receive, for example, a message that identifies the same route B4, but now the distance is, let's say, 2, and the sending bridge ID is, it could be even B12. So now since the distance to the route is smaller, so this message is better. Now if the route ID and distance both are equal, then the tie is broken in the favor of a smaller bridge ID. So now suppose that the message that it received here is B4, same route, same distance, but now the sender ID is, let's say, B5. And so now because the sender ID is smaller than what it had before, so this message is better than the configuration message that it has recorded as the best one so far. And if there is a tie on all these fields, so it may receive a message like, same B4, 4 and B5, but on a different port. So it could be a port, let's say port number 2, this might be port number 5, and so in this case this configuration message is going to be considered better. In case the new configuration message is better than the current record, then the bridge would replace the old information with the new. And when a bridge receives a configuration message from a smaller ID bridge, right, that is clear indication that it cannot be the root bridge, then it stops generating configuration messages on its own. And so it's only going to forward the configuration messages that it receives from other bridge or other bridges. Let's consider our old example one more time. So we had this bridge 1, 2 and 3 connected, and so they were connected in a loop, right? So in this case, from our discussion so far, this bridge has the smallest ID, so this is going to be the root bridge. And this root bridge is going to always forward frames over all its ports, right? So it's always going to have both of these ports forward frames. Now every bridge computes the shortest path to the root and notes which of its port is on this path, and that's called the root port for that bridge, right? So for this bridge 2, it can reach this route via this port as well as this port, and assuming that the cost is 1 on each of these links. And so clearly the distance to the route is less on going from this port, and therefore so let's just call it make it clear. And so this port is going to be the root port of this bridge. And similarly for bridge 3, the distance to the root is smaller via this port than this port, and so this is going to be the root port for again bridge 3. Now here is it's a little bit more involved example. So suppose there is a bridge called B16, so its ID is 16. It has 4 ports 1 through 4, and it receives these 4 messages on these 4 ports. So this is a message that is received on port 1, port 2, port 3, and port 4. And as you can see, the message on port 1 and port 4 identify a bridge with bigger ID than these 2 messages. So clearly so either these bridges have just booted later on, or it's in the process of conversion. So the bridges have not converged to a spanning tree yet. And so out of these 2 messages, right, the distance to the bridge, to the root bridge, right, offered by this bridge number 14 is longer than this one. So 14 already says that the distance to the root is 6 from me, and so from bridge 16 the distance is going to be 7, and on port 3 the distance to this root bridge is going to be 5, because the distance from 12 is 4, add 1, then that's 5, and therefore on this bridge at this iteration port 3 is the root port. And next to the root port there are 2 more kinds of ports that we have to know. This one is called block port and other one is called designated port. So when a bridge receives a configuration message from a bridge that is farther to the root, or it's equally far but from a larger ID bridge, then it becomes designated bridge on this port. And when a bridge receives a configuration message from a bridge that is closer to the root, right, so this bridge is farther than the message that it received, or it's equally far but the message is coming from a smaller ID bridge on a non-root port, then it blocks that port. So again, let's consider our previous example. So 2 is going to send this message 1 1 2 to 3, and 3 is going to send 1 1 3 to 2. Now 2 receives this message 1 1 3, and its message is better than what it receives, so this becomes the designated port. And so this port is the designated port, or this bridge is the designated bridge on this port. And in the case of 3, right, it receives a better message, right, so it's equally far but from a smaller ID bridge, and this port is not the root port, right, remember these 2 ports are the root ports. And so in this case it's going to block, right, so this is going to be a block port, and the consequence of that is as we said before, this link is pretty much like it does not exist, although this bridge 3 will keep receiving BPDUs on this link, but it's not going to forward anything on, from this port. Okay, let's work through this example. We have 5 bridges, B1 through B5, and we're going to assume that all these bridges boot at the same time. So they would all start off by claiming to be the root, right? So B1 is going to send something like B1 0 B1, and B2 is going to send B2 0 B2, and B4 is going to send B4 0 B4, and so on. Now let's focus on B4, right? So B4 will receive B2 0 B2, and now since the ID of the bridge that sent this message is less than its own ID, B4 will accept B2 as root. And so let me just show this. So B2 sent B2 0 B2 on this as well as this link. Actually it does. And B4 had sent B4 0 B4, suppose, but now it receives this, so it knows that there is a bridge with a smaller ID, so it cannot possibly be the root. And so as the result of receiving this B2 0 B2, B4 is going to add 1 to this distance, so it's going to say B2 1 B4, and it's going to send this on both of these links to B3 and B5. However, B3 is also going to receive this message, B1 0 B1, and so as a result B3 would accept B1 as the root because it has lower ID, and so B3 is going to send towards B4 and B5 this message B1 dot 1 dot B3. So as a result, B4 would know that B3 has better configuration than B4, and so we have to go through one more iteration. So either at this time it's going to be either a root or a block port. So we will see how it evolves in the next slide. Okay, so recall B3 had sent this message B1 1 B3, and B2 will get this message B1 0 B1. It's going to generate its own message sent to B4, and that would be B1 1 B2. Now given our rules, so the tie is broken on the third field, right? So B4 is going to accept B1 as the root now, and it notes, as I said, that both these B3 and B2, both of these neighbors are equidistant from the bridge. However, the ID of B2 is smaller, and therefore it's going to designate this port that connects to B2 as the root port, and it simply is going to block this port. And as for B3, the configuration message that B3 sends on this port towards B4 is going to be better than the configuration message that B4 sends, and therefore this port is going to be the designated port. But nevertheless, since this port is blocked, this link is removed from the spanning tree. and I leave it as exercise for you to verify that this link is also not going to be part of the spanning tree. And after that, it's easy to see that you get a spanning tree, at the end. And we will go over one more example. So suppose we have this bridge B16, and it receives these 5 messages on its ports, ports 1 through 5. So we'll just number 1, 2, 3, 4, 5. These are its ports, and it receives message 20, 0, 20 on this port, 10, 10, 22 on port 2, 10, 6, 14 on port 3, 10, 6, 12 on port 4, and 10, 6, 12 also on port 5. And so at this iteration, right, looking at the ID of the root bridges, 10 is the smallest that we have seen, right? So then out of these 4 messages, right, the last 3 messages identify the same distance to the root, right? And so from B16, from the sender, the distance is 6. So from B16, the distance is 7 to the root. Now again, for the case of for these 3, so the third tiebreaker is the sending bridge ID. So again, 12 is smaller than 14, right? So we look at these 2 messages, and out of these 2, this arrived at port number 4 and this arrived at port number 5, and so therefore port number 4 is the root port at this iteration. That's the best configuration message, and as a result, this bridge B16 will send out 10, 7, 16, but it's going to do that only on ports 1 and 2. Why? Because on port 1 it received a message that is inferior to this current configuration, right? So it identifies a bridge ID of 20 that is greater than 10, and on port 2 it received a message that identified a larger distance to the root, right? However, it's going to basically, so as I said, so on these 2 ports, ports 1 and 2, this becomes the designated bridge. So these are designated ports. This is the root port, and it's going to block these other 2 ports because its configuration message 10, 7, 16 that it would have sent, it's inferior to the messages that it received, namely 10, 6, 14 and 10, 6, 12. So this is going to block these 2 ports. And so we mentioned some time ago that spanning tree algorithm is dynamic in the sense that if there is any change in the network, the protocol would react to that change, and make adjustments. And to achieve that, even after the system has stabilized, the root bridge would continue to send these configuration messages periodically, and other bridges continue to forward these messages, right, after the changes that we discussed before. So when a bridge fails, the downstream bridges will not receive the configuration messages, right? And after waiting for some time, right, they are going to start from the beginning. So they are going to again claim to be the root and start the algorithm. The limitations of bridges is that they don't scale. And they don't scale firstly because a spanning tree algorithm itself does not scale. There is no provision to impose any kind of hierarchy. It's a spanning tree algorithm scales linearly with the size of network. And second, bridges would forward all broadcast messages, on all ports except for the incoming port. And so broadcasts don't scale. And that's because, consider a large network. So a broadcast that originated in one LAN, right, it's unlikely to be of interest in some other portion of network that's, distant, geographically distant from this LAN, for example. And another limitation of bridges is that they do not accommodate heterogeneity, because they look at frame header, right? So a bridge can interconnect an Ethernet LAN with another Ethernet LAN, or a tokening network with another tokening network, and they are actually able to interconnect Ethernet with Wi-Fi networks, because both of these use the same frame format. But if the frame formats differ, bridges cannot interconnect different LANs. So these are the limitations of bridges. One way to improve the scalability of an extended LAN is to use what is called virtual LAN. Virtual LANs partition an extended LAN into several logically separate LANs. And we just discussed that broadcast is a reason why bridges are not scalable. The case of virtual LAN, broadcasts that originate in one virtual LAN is not forwarded to other virtual LANs. In a virtual LAN environment, LAN segments and ports are assigned virtual LAN IDs, or they are also called colors. And actually, people apply, for example, colored stickers in front of ports. And the packets are forwarded only within the same virtual LAN ID. Here is an example of a virtual LAN with two colors, gray and white. So these are the ports with gray color, and then these are the ones with white color. And there is a practical reason, besides this scalability issue, why virtual LANs are used. In large campuses, or large companies, it's desirable that different departments use different LANs. For example, accounting would have a different LAN, human resources probably a different one, and then research and development could be another one, and then sales could be another one. And so one possibility is to just install different physical LANs, and that it's a very rigid thing. And other problem is that people move, right? And so what happens if a guy who was here, it's a, let's say, human resources guy, moves to somewhere here, and this guy who was research and development moves over here. And so we don't want to do too much of rewiring. And so virtual LANs are a great way to logically partition an extended LAN. And so in the case of this guy, for example, moving there and this guy moving here, it's just a matter of configuration where we designate this port to be a white, and this port to be part of the gray virtual LAN. And lastly, just note that for this VLAN to work correctly, some of the ports have to be assigned several colors. For example, this port has been assigned two colors, gray and white, and this port that connects to this hub is also assigned two colors, gray and white. The reason is that let's say there is a white broadcast that originates and it reaches this bridge B1. There are white colored stations on this part, and therefore those broadcasts have to be forwarded over this link. And there are also gray stations on this part, and therefore gray broadcasts also need to be forwarded here. However, any white broadcast need not be forwarded to this side because there is no white station that is attached to this bridge B1, and therefore the color here is only gray. To summarize, switches, or also called bridges, can be used to network hosts or to interconnect different local area networks. We saw that learning bridges learn the forwarding table from the source address in the incoming frames. And we also saw that spanning tree protocol uses a distributed algorithm, which is called spanning tree algorithm, to form spanning tree in extended LANs. And we also saw that a bridge with the smallest ID is elected as the root bridge of this spanning tree. And lastly, we saw that virtual LANs allow multiple logically separate LANs to coexist in the same physical LAN. The material that we covered in this video is discussed in detail in Peterson and Davis' book, Chapter 3, Section 1, and Tenenbaum and Witherall's book, Chapter 4, Section 8. Here is a short quiz for you. Find out which of the following statements is or are correct. You might want to pause this video. I will discuss the solution in the next slide. The correct options are B and D. A says that learning bridges learn the location of a host from destination address, and actually they learn from the source address, so that's wrong. If a learning bridge does not know the location of host X, it forwards all frames that are to be sent to X on all its ports except for the incoming port, and that's the correct behavior. In C, suppose bridge 12 receives these configuration messages 15.3.22, 14.4.18 and 20.0.20, and at this time it considers bridge 14 to be the root. So out of all these three messages, this definitely has the smallest root ID, but note that the ID of this bridge itself is smaller than this, so that's actually wrong. It knows that if there is no other bridge with a smaller ID than itself, then it's going to be the root. And the last one says, suppose bridge 25 receives 15.3.22, 16.4.21 and 15.2.20 on its three ports. Its port 3 is the root port, and so out of these three configuration messages, right, so these two have a smaller root ID, so they are better than the second one. And then this message has a smaller distance from the root than this one, and therefore this is correct. That's all in this video. See you next time.